This is video 2 in the chemical changes topic on GCSE AQA chemistry. It is a dual award topic, so it is valid for dual award and triple award scientists. Going to recommend you try the activities as you go through, pausing the video. So in this video, we're going to take a look at displacement reactions. Previously, we looked at reactions of metals that helped us to determine an order of reactivity. But when it came to things like iron and zinc that are actually very similar in reactivity, we realised it wasn't so clear. So we're going to use displacement reactions instead. We're also going to look at why carbon and hydrogen are in the reactivity series. We're going to look at what predictions we can make about chemical reactions based on position within the reactivity series. And we're also going to take a look at ionic equations and half equations. And finally, we are going to look at the concept of oxidation and reduction with the consideration of loss or gain of electrons. So at the bottom of this, we have an illustration of a displacement reaction. If A is the metal and B is a metal within a compound, then A, if it's more reactive than B, can kick it out. It takes its place in the compound. So a more reactive metal can displace a less reactive metal in solution. With that in mind, based on your knowledge of chemistry and your knowledge of the reactivity series, where do we think there will be reactions in the boxes within this table? Have a think and then review. Well, what you would actually find is that magnesium could displace copper in copper sulfate, zinc in zinc sulfate, and iron in iron sulfate. Copper, however, would not be able to displace the metal in any of them. If we were to look at zinc, zinc would be able to displace copper and would be able to displace iron, but it wouldn't be reactive enough to displace magnesium. And finally, iron would only be able to displace copper. So in terms of the question, why did we make these predictions? Well, it comes to the reactivity series. Remember, we have said a more reactive metal can kick out a less reactive metal. And if we put those into an order of reactivity, we can see it goes magnesium, zinc, iron, and copper. Now, the big advantage of this reaction is that we could see zinc displacing iron, whereas in the previous video where we reacted zinc and iron with acid, there were very similar observations. You wouldn't, with any great deal of confidence, be able to say that zinc was the more reactive of the two. On this one, we can. And then why did we not do magnesium with magnesium sulfate, copper with copper sulfate, etc.? And it is really straightforward. Why would I try to displace copper with copper or magnesium with magnesium? There wouldn't be any observations if a metal were to displace itself. We're not actually getting an overall chemical change. So we're going to move on and we are going to take a look at ionic equations. Now, as it points out on screen at the moment, you do need to know the charges on ions. You won't be provided with them. That's in many ways quite straightforward. All the group 1 form +1 ions, group 2 form +2, group 7 form -1. But you are going to have to remember things like sulfate being -2, etc. Now, in terms of building an ionic equation, what you have to do, and I'm going to put a model up on screen, is you can take a reaction, write out the full equation, but then you are going to break down anything that is ionic and aqueous. So if it's ionic and the ions are free to move, you're going to break it down into its ions. So we can see on the example here, magnesium, copper sulfate, magnesium sulfate, and copper. But the copper sulfate is an ionic compound and it's aqueous. So we break it down into a copper +2 and an SO4 2-. Similarly, we have MgSO4. It's aqueous and ionic. We can break it down into Mg +2 and SO4 2-. Now, what we can then do with an ionic equation is remove any spectators, anything that does not change in a chemical reaction. And you can see here that SO4 2-, AQ, appears on both the left and the right. So we get rid. And we then write the ionic equation, as we can see at the bottom, without those spectators. So with that in mind, have a go at doing these three. So first thing with number 1, I'm going to break down my zinc sulfate and my magnesium sulfate because they are ionic and they are aqueous. When I break through that, I can see that I've got an SO42- here and an SO42- here. So I'm going to get rid of them. And that then allows me to write the overall ionic equation. Mg solid plus Zn plus 2 Aq goes to Zn solid and Mg plus 2 Aq. State symbols on these are incredibly important. Have a go at number 2 if you haven't already. Again, hopefully you're seeing a pattern here. The copper sulfate and the iron sulfate can be broken down. We look for spectators. Once again, it's sulfate ions that we get rid of, and then we simply write the equation out again without those sulfate ions. So we have our iron, our copper ions going to copper and iron ions. Finally, a third one. And once again, I write it out. I can see my iron sulfate and my zinc sulfate have been broken down into their constituent ions. I've got SO42- as spectator ions on the left and the right. So I get rid, and then I rewrite the equation without them. And there we have it. So we're going to move on to a slightly different area now, and we are going to consider why hydrogen and carbon are in the reactivity series. We discussed this in the last video, but why does it seem odd that they are there? The simple answer is that they're not metals. This is the reactivity series of metals, and we're including non-metals in there. So there must be a really important reason for that. And there is an important reason. We know, or we need to know, something about the chemistry of the metals above and below carbon in the reactivity series and above and below hydrogen in the reactivity series. See if you can come up with what those properties are. So we're going to see this in a later video, but metals below carbon can be extracted from their ores by it. Anything above can't be, and we move into using something called electrolysis, which we have a topic on later on within the course. And hydrogen is a really important one because any metals above hydrogen in the reactivity series will react with acid, but any below will not. So we're now going to introduce the concept of oxidation and reduction. And we might think of oxidation as gaining oxygen and therefore reduction as losing oxygen, but we need to think about it in terms of transfer of electrons as well. And this mnemonic is really important. If you know it, test yourself on it. If you don't, you can watch through and it's going to be helpful if you can learn it. So oxidation is loss of electrons. And we'll look at what that looks like in equations in a moment's time. But if oxidation is loss of electrons, reduction is gain of electrons. That's an incredibly important piece of information to take forward. Okay, we're going to finish off by looking at half equations. Now, these take a step beyond what we did with the ionic equations earlier. So we can see here that from earlier in the video, we've taken our magnesium and copper sulfate, changed it to magnesium sulfate and copper. We've reacted, and I have simplified. I've broken down into ions where I can. I've got rid of spectators, and we now have Mg solid plus Cu plus 2 goes to Mg plus 2 and Cu. Now, half equations take that a step further forward. They will break it down into two component parts. I'll want a half equation that relates to what happens to magnesium and one that relates to what happens to copper. And we can see that just down here. Mg solid goes to Mg plus 2 aqueous, and Cu plus 2 aqueous goes to Cu solid. Now, we know, we have seen these equations way back in the atomic structure topic. And we can balance charge in these equations by adding electrons. So on the magnesium, I have a charge of 0 on the left, I have a charge of plus 2 on the right. So I add 2 electrons on the right hand side to bring the overall charge to 0. And I've completed my half equation. On the copper, I'm adding 2 electrons on the left hand side. And what we can also do is take what we know about OILRIG oxidation is loss of electrons and reduction is gain of electrons. And I can see here that copper 2 ions have gained electrons. So this is reduction. The electrons are added on the left-hand side. In the one above, magnesium has become Mg plus 2. But it's lost 2 electrons to do that. So this is showing magnesium being oxidized. It's the process of oxidation. So have a go at these 3 to take us to the end of this video. And for number 1, straight away, I'm going to jump to the Ionic equation. So I've already broken down into ions and removed my sulfate spectators. I now need to put together my 2 half equations. So my Mg becomes Mg plus 2, my Zn plus 2 becomes Zn. You'll notice I'm including state symbols at every opportunity. Very, very important. Now, how am I going to balance it? Well, my charge on the left with magnesium is 0. On the right is plus 2, so I'm adding 2 electrons on the right hand side. And on the zinc, I'm adding 2 electrons to Zn plus 2, that's an overall charge of 0, going to an overall charge of 0 on the zinc. If we take a look at the position of the electrons, just to reinforce what we saw in the example, magnesium has lost electrons to become Mg plus 2, so it's oxidation, whereas zinc ions have gained electrons to become zinc, so that's reduction. Next example with iron and copper sulfate. And once again, I've broken it down to its Ionic equation, and we can now split this into the 2 half equations. My iron becoming iron 2, and my copper 2 becoming copper. And I have those here, still with state symbols. Now again, I'm hoping you're seeing patterns here. The Fe plus 2 is going to have 2 electrons added on that side. I now have a charge of 0 on the left and an overall charge of 0 on the right. In the copper 2, I've added 2 electrons on the left, which allows the copper 2 to be reduced to copper. And again, just to reinforce, electrons lost, this is an oxidation half equation, and reduction, gaining 2 electrons for the copper 2. Final example. And on here we have got zinc and iron 2 going to iron and zinc 2. I break it down, my zinc going to Zn plus 2, my iron 2 going to iron, state symbols included all the way through. And how am I going to balance the charge? Well, I'm going to add 2 electrons on the right on the top one and 2 electrons on the left on the bottom one. My overall charge is now 0 on the left, 0 on the right, 0 on the left, 0 on the right. And again, just so we can see very, very clearly, zinc has been oxidized because it's lost electrons, and iron 2 ions have been reduced because they've gained 2 electrons. That takes us to the end of this video. Thank you for listening, and goodbye.